section of your plane geometry, okay, or circles. So that will require us to recall, okay, all our circle properties, which I have already summarized for you in page 4 and 5 of your notes. Okay. One new thing that I will introduce later on is this alternate segment theorem. Okay, so alternate segment theorem, even if you see it in AMATS, okay, as in you want to use this property in EMATS, sorry. Okay, if you want to use this property in EMATS, you can do so. Although usually you don't require using alternate segment theorem. Okay, but in AMATS, whenever you are given any circles to actually go about proving, okay, we will usually require alternate segment theorem. Okay, but we will start off by not using it first, okay, because the questions don't require it. So I'll come back to it in a moment when I want to introduce questions involving that. Okay, so let's look at example 9. We are given this diagram where O is the center and AB is the diameter of the circle. Given that OX is parallel to BC, we want to prove that OX is perpendicular to AC. Okay, so this indication that I made in black is what we want to actually go about proving. Now, whenever we are given circles, okay, and we want to introduce any 90 degrees into the circle question, because in the original question itself, there's no 90 degrees being mentioned. Okay, there are generally two ways that we can do so, okay, to bring in 90 degrees. What is one property that will involve 90 degrees for circles? What we have? Ashley? Yeah? Okay, right angle in semicircle, right? Okay, so we have this property whereby we need a diameter, okay, and then we get our 90 degrees introduced into the question. Okay, another way that we can do so is tangent perpendicular to radius, right? Okay, so tangent perpendicular to radius. So if you have a circle, sorry, my circles are not that perfect. Okay, but if I have a radius and a tangent, okay, that's how a 90 degrees can be introduced to it. Okay, and 90 degrees is very often being used, okay, in your circle question. Right, so there's some kinks over there. Okay, so now in this case, there's no tangent involved, so very likely we will not be using this. Okay, we will be making use of right angle and semicircle. Why? Because the question has already mentioned that AB is a diameter. Okay, so with AB being diameter, we know that this is going to be 90 degrees. Right? Okay, and because the question has already told us that OX is parallel to BC, okay, by your corresponding angles, parallel lines property, we will see that this 90 degrees can be transferred over here, and therefore that's how we get our 90 degrees. So the proof is actually not that long. Okay, so let's write that down. Angle you can label the diagram for convenience of presentation. So because there is no label for this vertex over here, you may want to just label it P. So you can label that in your question paper when it comes to exam also. Okay, just label directly into diagram. So we call that APO, being 90 degrees as well, due to your corresponding parallel lines property. Okay, you may notice that my presentation answer is slightly different. It deviates away from the since and then structure, but it does apply since because of this evidence, then OX is perpendicular to AC. Okay. is that AB is a diameter with center O, and then DC is parallel to AB, and DB and OC intersect at E. We want to prove that angle BEC, which is this angle over here, is actually 3 times the angle of ABD. So ABD is this angle over here. So to keep my objective clear, sometimes I will label it in my diagram. I want this to be 3 times, so I'll just draw 3 strokes up. Okay? So that I have the diagram to help me, okay, to identify the end result that I want. Okay? This is slightly complicated. First of all, do I actually need right angle and semicircle in this case? We don't. So even though the question did mention AB being a diameter, there is no visible triangle, or rather we can form one, but introducing the 90 degrees isn't helpful because the end result doesn't require us to have any 90 degrees at all. Okay? The end result wants us to have 3 times of something. We know of a property that can bring in 2 times of something. Right? Okay, angle at center equals 2 times angle at circumference. So we know this property. Okay, so it helps us to multiply a certain angle. So maybe this property won't be helpful. Okay. Furthermore, we are given the center. Okay, so we can identify an angle at the center and angle at circumference. Okay. Now, other than that, we also know that there are parallel lines. Okay, so with the parallel lines, we can see a Z shape. We can see our alternate angles. So I know that this angle is equal to this one. Okay, so at least we know that. Okay, we write down the things that we know first. Right? Another thing that we know is the angle BOC, which is an angle at the center. Okay, maybe I should use a different color. Angle BOC is an angle at the center itself. Okay, and it is subtended by this chord over here. Okay, so it forms this triangle here. And with this same chord, right, it brings us another angle, okay, that is at the circumference. Do you all see that? Okay, so the angle at the center over here is actually 2 times this angle. Okay, so maybe just to indicate the 2 times factor idea, okay, I just indicate 2 strokes up. Alright? So this is the objective that we want, right? So how then, okay, do we see that this angle is going to be 3 times of this? Okay, a helpful property for us to remember about triangle is the exterior angle of triangle property. Okay, it is in your notes. It does help us to save a little bit of time by remembering this property, which tells us that the angle that is outside of the triangle is equal to this angle plus this angle. Right? So what do we see over here is that with this triangle, okay, if I were to extend it out like that, do we see that this triple angle that we want, okay, is actually the exterior angle of this one plus this one. So if this is double and this is single, this adds up to be 3. You all see that? Okay. I know that at the beginner level, it is not going to be easy for us to see this, okay? But that's why I'm telling you that, okay, when we want triple angle, maybe we think about certain properties that will help us to increase it in size, okay? And then also making use of any other fact that we already know. In this case, the alternate angles idea. So now let's write down the formal proof, okay? Okay, I'm going to let angle ABD equals to X. That will give us a lot of convenience in terms of our presentation. Because otherwise, you're going to tell me ABD equals BDC, and then after equals to that, then very difficult for us to link eventually. Okay, so angle ABD is the base, we let it be x. We know that angle CDV is equals to x also due to your alternate angles, parallel lines. That was the first thing that we observed. Okay. And then we talk about how this is actually double of this. So angle BOC equals to 2x. Okay, because of your angle at center equals to 2 times angle at circumference. And therefore, angle BEC equals to angle BOC plus angle AB equals to 2x plus x. And that is equals to 3x. Okay, so I find that doing this makes the presentation neater. And therefore, we conclude that angle BEC equals to 3 times of angle AB. Questions? Right, let's move on. So in example 11, given a very clean diagram, no information, no values given to you at all. Okay, they only show you different chords, and then they want you to actually prove that triangle JML, okay, which is this small triangle here, is actually similar to JKN. Okay, JKN being the one observed, right? In this case, I want us to make sure that we are aware that JML is in this manner, but JKN is the other orientation. So don't fall into the visual trap to think that this triangle is similar in the same orientation to JKN. So do observe, okay, how the naming is being done. Okay, so that's something that you need to pay attention to. That's why, okay, we should probably have a habit of drawing out the triangle to ensure that we do not get lost in the visual trip. Okay, JML is supposed to be similar to JKN. So it's a different orientation to what is being presented. Okay. Now the very easy thing that we can identify, okay, just from the diagram alone, okay, for similar triangles, is that we know that J is a common angle. Okay, we definitely can eliminate the fact that using sides is not going to be a feasible proof, okay, for this question at all. Okay, because there's no given information about the length at all. You cannot use the information in part 2 to help you in part I. It must go in sequence. Okay? So therefore, we must be relying on AA similarity test. We have one pair of corresponding angle already. Now the task is to find out, okay, the other pair of similar angles, or rather same angles. Okay, so we know that one pair will either be M and K. So M is over here and K is over here, and the other pair would be N and L. Okay, so which pair would be easy for us to actually go about proving? Okay, and how do we actually show that they are going to be equal? Right? So, hang on, so actually I also need to think one, even though I wrote it out. T minus N. Okay, we will make use of our NKJ as well as our NKJ and LMG. Okay, so we focus on that. How we do that is that NKJ is equals to 180 degrees minus away angle NML. Okay, why? That's because of your angles in opposite segments. Okay, so if you recall how to identify your cyclic quadrilateral, if I'm able to have a quadrilateral whereby all the 4 corners are on the circumference of the circle, okay, the opposite sides, or rather opposite angles, okay, will have to add up to be 180 degrees. So we know that this angle and this angle add up to be 180 degrees. Hence, I wrote NKJ is equals to 180 minus away this angle here. Okay, and that property is your angles in opposite segments. Okay, so let me just write this down. If this is x, this is 180 minus x. Okay, I'm trying to prove that this is equals to this. Okay, and I hope that you see that if this is 180 minus x and this is on the same straight line, then this will have to be x because of your adjacent angles on the straight line. Exactly the same over here. We see that our NKJ is equals to LMG. Okay, so these two angles are equal. Right, and then just now the one that is given. So we write that down. In case you're wondering, could you do it with the other angle? We need to say the angle at L and the angle at N. Okay, you can do that. So the angle at L is this, angle at N is this one. Okay, so the same thing actually applies. Using your angles in opposite segment. Way of writing, okay, or answering the question, where you use the other pair instead. Okay, so it doesn't matter in this particular question which pair of angles you're choosing. Of the lengths that we're given. So Kn is given to be 3 cm, Lm is 1.5, Jm is 3, and Kj is 6. Okay, so we want to show that Kj is 6. Okay, so if you have drawn your triangles in this manner, it will be a very quick task. Okay, if you don't actually draw it out, relying on this visually, it can be very challenging to see in your brain itself. So I really recommend that you draw it out, okay, because I can see very clearly how it corresponds. Okay, so since I'm trying to find out what is Kj, the corresponding sides to, corresponding side to Kj is Mj, which is equal, okay, to Nk over Lm. Right? Since the two triangles are similar. So you can put in the numbers. Nk is 3, Lm is 2. Okay, and then take a minute to read example 12 as I erase the whiteboard. and KC are tangents to the circle at A, B, and C respectively. So since we're given tangents, we will use properties related to tangents. Okay, one important property is your tangent perpendicular to radius. But in this question, no radius is being given to us, so we will not be able to use that. Another important one is tangents from external point. So if you look at your notes, there is one that says tangents from external point. Okay, and what tangents from external point tells us is that the two tangents that comes from anywhere on the circle, when they meet, okay, it will be such that PA and PB are going to be equal in length. Okay. Likewise, for the tangent PK and KC, when they meet, your BK is equals to KC. Okay, and that is helpful because in part I, we want to show that triangle PAB and KBC are isosceles. Right, so we will be making use of that property. Okay, so let's answer part I first. So we have proven that. In part 2, we want to prove that AB is perpendicular to BC. So we want to show that this is 90 degrees. While the diagram looks as though AC is a diameter, we cannot assume that AC is a diameter because that's what you want to prove in part 3. In fact, your solution to part 2 is meant to help you to answer part 3. Okay, so how do we go about showing that AB is perpendicular to BC? Okay, one other information we have not yet used is that APK, which is this angle here, plus angle BKC, this angle here, they add up to be 180 degrees. Okay, so we have to make use of that information to help us show that this is going to be 90 degrees. Okay. First of all, we are aware that triangle PAB and triangle KBC are isosceles. Okay, so we can note that the base angle will be 180 degrees minus away angle APB and then divide by 2. Using your base angles of isosceles triangle property as well as the angle sum of triangle property. Okay, same thing can apply for the other isosceles triangle. Whereby I can figure out an expression as such over here. Okay? Because at this juncture, okay, I really don't have much information, right? Then I'll just write down what I know first. Okay, so sometimes that will help. Okay, just write down what you know first. Okay. But of course, I know the answer lah, right? So why I choose intentionally PAB and KBC? Okay, that's because, or rather instead of PAB, maybe just to be helpful, PBA and PAB. Okay. PDA is this angle over here. Maybe I should choose green color. And then our KBC is this angle over here. Okay, we see that this angle plus this angle plus this angle will definitely form on a straight line and they will add up to be 180 degrees. Okay, so we're going to do a little bit of algebraic manipulation of some sort, okay, in order to show that this is going to be 90 degrees. Okay, and also making use of this information that we are given. Okay, so how that will look like? First write down the thing that we know that they are on a straight line. And then we can make the subject of ABC, which is 180 minus the way angle PDA minus the way angle KBC. I already have an expression of PDA and I also have an expression for KBC. Okay, so I can write that in. And then the next few steps will be a matter of your algebraic manipulation. Continue it over here. I make the two fractions have the same base of 2. First fraction on the left will still remain as 180 minus angle APB. Take note there are minus signs outside of the fraction. Okay, so essentially when I combine it in the same fraction, I have factorized out the minus 1 already over here. Okay, so it should actually be plus 180 degrees minus away angle BKC. Right? Yep. Okay, because this minus sign has already taken out, so we are just keeping the things on top of the numerator. Okay, because they are all the same sign. Okay, and then 180 plus 180, that's 360. I factorize out the minus, I'll be left with angle APB plus BKC. Oops, APB. Okay, and APB plus BKC, what are these angles? Where are these angles? It is this angle over here and this angle over here. And we know that they add up to be 180 degrees. And therefore, we get our 90 degrees. Okay. I know I may have made it look very easy, that it comes very natural to me. I want to tell you it doesn't come naturally to me either. It does take me some time to look and figure out how to write it out neatly as well. Okay? So it is not easy, okay, to actually plan it out as well. Okay, so it will take some time of figuring out the diagram, making markings here and there, okay, and then having all the pieces of information and then putting it all together neatly. Yeah, Jasper. This one? Because, okay, you sit down and how, huh? It is because, okay, I erase this part on top, I think this part on top, everybody gets it right? Okay. We can see the equivalent is 180 degrees minus away, if I put brackets around it now, APB over 2 plus 180 degrees minus angle BKC over 2. We agree with this statement? From here to here, I factorize out, right? Negative sign when I put brackets. So that's why this one must be a plus. So now, addition of two fractions together that has the same denominator, it will be plus 180 degrees. Plus and minus remains a minus, alright? Okay? Okay. And then I know that I can remove the brackets, but it doesn't matter because the minus still stays outside of the fraction. So that's why we have this. Okay? Any other questions? Right? And then part 3 is just a single liner. Since we already know the angle ABC is 90 degrees, then by right angle in semicircle property, AC is a 90. Okay? So the challenge of this question is really in part 2. Requires us to know our alternate segment theorem. So let me introduce the alternate segment theorem to you. Okay. In some other books that you may read, I'm not sure whether you read other maths books at all. Okay. You may call this tangent chord theorem as well. But most of the time I will call it alternate segment theorem. Okay. For the acronym, or rather the abbreviation of it, your word alternate, you can write it as ALT dot, that's fine as well. Or you want to write it in full, also okay. Okay. So I usually have to have it all write it in full, so that's why I wrote it like that. Okay, so what does it say? It says that there must be a tangent. Okay. First thing that you must observe, there must be a tangent, and there must be a triangle whose vertices are all on the circle itself. Okay, so this triangle, all the corners must be on the circle, and then the tangent must be out of one of the corners, okay, of the triangle. Okay, and then how is it alternate? Okay, it is based on this angle over here that is alternating from here, okay, that are going to be equal. Alright, so we can have this angle equal to this angle. That is what alternate segment theorem says. Must have tangent, must have triangle, all the corners on the circle. Okay? So, naturally with this understanding, there is also another pair that we can observe out of this diagram that I didn't write in, which is this angle over here will also be equals to the angle on the outside of the triangle and to the tangent, this angle. So this angle and this angle are actually also equal to each other based on your alternate segment theorem. Okay, so angle PBA equals to angle, if I have this as S, PAS. Right? So that is what your alternate segment theorem says. Okay? Right? Of course, a tangent need not always be a horizontal line. So just to provide us with different orientations. Okay, so don't be fixated on seeing things in one manner only. Okay, so even if my circle being this way, having a triangle like this, okay, the center placement doesn't matter actually, so long as you have a triangle. And let's say I have a tangent here. Okay, so what are the two alternate angles that we can have? We can have one being here, another one here, right? Okay, and then the next one being this one with this one. So angle on the inside, angle on the outside. Alright, so there's another way that you can see things. That's the alternate segment theorem. Okay, clear? Let's do a question. Okay, in this diagram, there are points A, B, C, D that lie on the circle. The lines Q, A, T, and P, B, T are tangents at A, B respectively. Q, D, C is a straight line and is parallel to A, B. Okay, it is very important for us to not be confused with recognizing C, D, Q as a tangent. Very often people tend to misinterpret or get confused that CDQ becomes a tangent itself. Just because it is a line that goes outside of the circle, it doesn't mean that it is a tangent. Tangent must be at one point of the circle only. Okay? So QDC being a straight line, it is also parallel to AB. In part I, we want to show that triangle ABC is similar to ADQ. So ABC being this, ADQ being this one. Okay, so maybe it will be helpful for us to again draw out the two triangles in the same orientation. So ABC, ADQ. Okay, just for cleaner diagram, I mix this up. Right? So how are we to determine that they are going to be similar? Because there is actually no common angle. Okay? So first of all, we recognize that there are tangents. So when there are tangents and there are triangles, we observe that there are two triangles inside the circle. One being ABC, the other one being ADC. Okay? We can recognize our alternate segment theorem first. Okay? Or apply our alternate segment theorem. Okay? Since our focus is on triangle ABC, and our focus is also on AQD, so we focus on this tangent over here. Okay, we can see that one pair of alternate segment is this part. Okay, another one is this angle over here. Okay? So one of the angles that are being identified is this angle B. Okay, we want to figure out a way to show that it is equal to this angle Q over here. Angle D, not angle Q. My bad. Okay, yep, deviant angle. Okay, so how could we show that this angle is equal to this angle here? Okay, so let's maybe just write down what we already know first. EAQ. Wait up. ACE. Sorry, hang on. Let me refigure this out again. Sorry, my bad. Okay. Anyway, we just identified the alternate segment theorems. Okay. So that's one way that we can see it. Just change this to red. Okay. Another way that we can see it, since there are two triangles, right? Okay. If we have this triangle, what is it that we can see? We can see that this angle here, okay, is equal to this angle because of the triangle and the tangent here. And then after that, this angle is equal to this angle here. Your diagram can get very messy, right? Alright? So that's why I use pencil. Okay? In your exam, please use pencil on your diagrams. If you use pen, then there's no reversal of your markings really. And then it will just be very messy and you get very confused yourself. Okay? I find that these two angles here may not that helpful, so I'll just erase them. Okay? So we have identified that this and this green one are equal, this and this green ones are equal. Okay? We also know that because they are parallel, this angle here is equal to this angle here. Right? Okay, so this equals to this, equals to this. This being alternate segment theorem, this being alternate angles, parallel lines. Okay? So this angle falls in the triangle that we are looking for, which is at A, this one here. And this other one falls in the other triangle, which is also at A, which is this one over here. So at least we can tell that these two angles are equal. Okay? So let me write that down. ACD equals to angle DAQ. Alternate segment theorem. And then angle ACD equals to angle BAC. Okay, so at least we got one pair of angles out of the way. Okay. Any questions at this juncture? Okay. Sorry that just now I confused you with this rate alternate segment theorem with angle. Okay, but that is usually how I would go about figuring out my answer as well. I try to figure out what are all the equal ones first. Okay? And then I would realize that this and this is actually not that helpful. Okay? So I need to think of another way. Right? Now notice that this A, B, C, D is after all a cyclic quadrilateral also. Okay? We have altered out, we have angles in opposite segment. This and this angle, they add up to be 180 degrees. So let me just erase this one. Okay? And then this angle is actually on the same straight line as this angle over here. Because adjacent angles on the straight line. So there is a way for us to connect this to this and then to this. Because there's this connecting angle over here. Okay? So let's write that out. We said that angle ABC plus angle ADC equals 180 degrees. From here, okay, if let's say I do my simultaneous if you want to, or if you want to present it other ways, also can. Okay, because they are equals 180 degrees, the two statements are equal, and then our angle ADC does get cancelled out, so called. And therefore, angle ABC equals to angle ADQ. Okay, so I'm going to backtrack and write down the word since at the top. Okay, so we have proven the two angles being corresponding and equal. Okay, so I'll just write down properly again. Since angle DAQ equals to angle BAC and angle BAADC is equals to angle ADQ, then triangle ABC is similar to triangle ADQ. For English. Okay, part 2 I will continue with it on next Monday. Okay, example 14, it is fairly straightforward and manageable. So I want you to go back home and try out example 14. Okay, on your own. It really isn't long. Part I is only just 3 statements, and then part 2 is also 3 statements. Okay, so it isn't long at all. Alright, it is only example 13 that is slightly more complicated. Okay. So, go back home, try out example 14. Next Monday, I will finish out part 2 and I'll also finish out example 14.